we have found out that lambda 1 is equals to 0.46 and lambda 2 is equals to 0.42. Putting these values in A minus lambda I, we get two matrices. One is for substituting lambda with lambda 1, and second one we get substituting lambda with lambda 2. These two matrices A minus lambda 1I is equals to minus 0.262, 0.021, 0.021 minus 0.218. This is first matrix, and the second matrix will be A minus lambda 2I, which is equals to minus 0.222, 0.021, 0.021 minus 0.178. From this matrix we'll compute the eigenvectors for lambda 1. From this matrix we'll compute eigenvectors for lambda 2. First we will compute the eigenvector for lambda 1. For that, let us assume that U, the eigenvector, is given by a 2 by 1 matrix, and U1, U2 are the components of the eigenvector. To compute the eigenvector U1 and U2, we will put this matrix here. Then we will put the value of U1 and U2 here. Then it will equalize to 0, 0. 0, 0 is the 2 by 1 null matrix. To solve this equation, we will multiply this component with U1, this one with this one, and we will add it. This is equation number 1. This is equation number 2. Solving equation 1 here, we get minus 0.262 U1 equals to minus 0.021 U2. Minus minus cancelled out, and then we get U1 divided by 0.021 is equals to U2 by 0.262. So from here U1 is equals to 0.021 and U2 is equals to 0.262. So our unit vector, our eigenvector U1, U2 is equals to 0.021, 0.262, which is equals to eigenvector U, which represents lambda 1 is equals to 0.46. Similarly, if we solve the equation 2, solving equation 2 also we will get different values of U1 and U2, and this also represent one of the eigenvector that represents U1. But however, we in this case we will consider the eigenvector with the values of u1 as 0.021 and u2 as 0.262. Following same method, we can also find out the eigenvector for lambda 2. However, in this case, we are interested to evaluate the eigenvector only for one component, that is lambda 1, which is the maximum of these two values, lambda 1 and lambda 2. And we got the eigenvector as, for lambda equal to 0.46, we got the eigenvector u as 0.21, 0.262. With this value of eigenvector, we will compute the next step for the computation of PCA. Next step is normalize the eigenvector vector u. To normalize, we will perform this operation. U is equals to 0.021 divided by square root of 0.021 whole square plus 0.262 whole square. Similarly, the second component will be 0.262 divided by the same term, square root of 0.021 whole square plus 0.262 whole square, which gives us the value 0.0798 and 0.9961. So this is the normalized eigenvector. This is normalized eigenvector. After computing the normalized eigenvector, we need to perform the next step for the PCA evaluation. After normalizing the eigenvector, we get u as 0.0798, 0.996. With the normalized eigenvector, we are next to compute the new data points. For the computation of the new data points, we have to go back to the earlier table of data which was given to us, x and y. Then we also found out the x bar and y bar, which is the mean of x and y. This x bar is computed as x bar is equal to sum of all xi's from 1.3 till 1.9 and divided by total number of elements, that is the sample size. Similarly, y bar is also computed as sum of yi divided by n, and this value leads to 1.66 and this one is 2.42. And then we need to compute, as we have told earlier, that from these two features of the given data set, we have to find out one feature that contributes much to the classification, and out of that, this x and y, we have to find a principal component, first principal component, or the principal component. In this case, there is only single principal component, and for that we have computed all the necessary things. Now the time to compute principal component for the given data set. First of all, this principal component, the first component of the principal component 1 is called PC11. We have denoted it as PC11, PC12, PC13, that way. So let's see how to compute PC11. To compute PC11, we will perform the operation U transpose. U is a matrix of 2 by 1, order 2 by 1, into, we'll take the element xi minus x bar and yi minus y bar That means here it is xi minus x bar. This value is nothing but u transpose will be there, and this matrix is minus 0.57, and next component is minus 0.72. If we multiply this matrix by u transpose is 0.0798. From here, transpose, if u is equals to this one, then u transpose will convert row into columns, 0.0798 and 0.996. This matrix will come here, 0.996. Then we will multiply it with minus 0.57, 0.72, minus 0.72, and it evaluates to a value of, this is equals to 0.0798 multiplied by minus 0.57 plus 0.996 multiplied by minus 0.72. This is equals to minus 0.763. So this component is minus 0.763. Next component also can be computed using the same technique, u transpose into the value of x minus x bar, which is minus 0.67 and 0.08, which is equals to 0.026. This value is equals to 0.026. Other components are also calculated, and the new values of the principal component are, the first value is 0.763 minus 0.763, 0.026, 0.648 values are given as a new principal component 1, and all the values starting from minus 0.763 till the minus 0.117. These are the values of the new, or these are the new data points in the dataset, given dataset. This is derived using PCA. Now in the next step, we will see how to plot these values in a visualized form. For that, we will plot all the points in x and y, and x and y plane, two-dimensional plane, and we will see how they look like, how the new dataset looks like. Till now, in the process of PCA evaluation, we have found out that the principal component PC1 is derived as the points given here. These are the points derived as a PC1 component of the given dataset xy. Here x bar is 1.66, that is mean of x is 1.66 and mean of y is 2.42. Now it's time to represent the data points which is given by PC1 for visualization in two-dimensional space. For that, what we need to do, this is the origin of the given data set for xy. This point, since we wanted to plot the PC1 values, that's why this point to be moved to another, this origin need to be moved to another point with x bar, y bar as origin. X bar is 1.66, 1.66 is somewhere here say, and 2.42 in the y-axis. 2.42, this is 2.42 is somewhere here. So if we put this point, if we plot this point, this will be somewhere here. This is the new origin of the data set. This is the new origin for plotting the PC1 components, and this one is given by 1.66 comma 2.42, and we will draw the x-axis and y-axis this way. This is new x-axis and this is new y-axis, and this side it is negative values of x, this way it is positive value of x. So this is new x and y axis, and now we have a eigenvector given as 0.079, 0.997. Let us plot this number, and in the new axis we are assuming that this is 1 and this is y in the y-axis, this is a 1 in the x-axis, 1 unit. Similarly, this is here somewhere here, it is the second unit, and this is here second unit. Now 0.079 is somewhere here, and 0.997 is somewhere here, and if we plot this point, then we get a point here. This is the location, of the eigenvector 0.079 comma 0.997. This is the point eigenvector. Now if we join the eigenvector with the origin like this, and if we extend this line here, this is our eigenvector u1, which is represented by this eigenvector, which was calculated from the highest value of lambda 1, which is 0.46. Once we get the eigenvector u1, next step is to place these points, the PC components, on the unit on the vector u1. To plot the PC values on the eigenvector, we need to find out the points in the points on the eigenvector. So first point is 0 minus 0.763. This is the origin. To put the values of PC1, components of PC1 on the eigenvector, we need to find the origin. If I extend this line a bit forward, the point where it will cross, that becomes the origin of the unit vector. We can set it as 0. Then we need to plot minus 0.763, the first point, minus 0.763. If I consider this one is the origin, then somewhere here, if we assume this is 1, similarly on the other side, this one will be 1 in the positive side, this is 1 in the negative side. So what we will do here, 0.76, this point may be considered as a point minus 0.763, then another negative point minus 0.5, one more negative point is there, minus 0.332. 0.332 is somewhere here, minus 0.332, and all other positive points we can put here, 0.803 if it is 1, positive 1, and somewhere we can put 803, and that way all the points are placed over the eigenvector u1. So these are the new points for the PC1 component. These are plots. Moreover, we have found out that we have evaluated two values of lambda. One is 0.46, another is lambda 2 is equal to 0.42. Certainly, for computing the eigenvector for lambda 2, we will get some eigenvector of this type, and that will be perpendicular to the unit vector or perpendicular to the eigenvector u1, and we'll take the point where the origin is considered for u1, and we can place one line eigenvector which is perpendicular with eigenvector u1, and that gives the eigenvector u2. So since we have not computed the values for eigenvector representing lambda 2, so simply we are putting this eigenvector u2 to show the placement on the plan. It shows the new data points on the line eigenvector u1. So with that, the PCA computation for a given data set x with having x and y with two independent variables, it is converted to one independent variables which carries most of the information of the data set, and this is placed over the eigenvector u1, and all points are shown here, and let's end the PCA evaluation of the problem stated.